So let's talk about the paper. This doesn't look immediately like a chapters 1 through 3 paper. And honestly, it does involve a lot of advanced inorganic chemistry. Again, just like with the PCA, there's some of this stuff that I don't intend you to get into. But the one thing that might look familiar is if you look at this set of 6 metals. This was exactly on the bottom of some of our graphs, especially in chapter 2 when we talk about the central graph for the whole thing. These 6 metals are on it in this order. And so this is the Irving-Williams series. And in fact, you can see that they, right here, they even refer to the Irving-Williams series. Have I mentioned that Williams, when he found that series, was doing undergraduate research? He was in Oxford at Merton College, where Professor Tolkien was also teaching. But he was doing with Professor Irving. He was doing research, and he came up with this thing that still carries his name. So, but what they found is that what they're doing is they're doing something with CO binding to metals. And they found the Irving-Williams series again. This is the complex stuff that they're doing. They make these frameworks, and they actually, I'm really jealous of inorganic chemists because they can crystallize pretty much anything they want, and they can get a crystal structure like that. For us biochemists, it's hard to get crystals. I mean, those of you who've tried know that it can be tricky to get crystals, and crystallization is trivial in organic chemistry, but in biochemistry it's really hard. But it was easy enough for them. They were able to get crystal structures of all these things, and they're studying how these bind to carbon monoxide, how these frameworks bind to CO, with the idea of, I think, coming up with some kind of way to actually bind the CO and get rid of it reversibly and at high capacity. Seems to make sense. It's naturally sticky. And because it's naturally sticky, it followed the same universal pattern of stickiness that we see in biology as well. When they're talking about bonds, because they have crystal structures for each of these 6 metals put into the framework, bound to CO, they have bond lengths and bond angles, which is really cool because we can talk about distance, which we usually can't in chemistry. Usually we're talking about kilojoules. Here we can talk about distance. And so they can measure things like different binding strength. And if you look at this, you can see that the binding strength follows the general Irving-Williams series. These, they have the different colors here, and they have, if you ever forget what the order of the Irving-Williams series is, just remember, look over here, and just follow this: manganese, iron, cobalt, nickel, copper, zinc, in that order. So manganese, and you have magnesium, which is actually way off to the far side, but when you get to the transition metals is what we're really talking about. You have manganese, and then you have up iron, and then a little bit higher nickel, a little bit, iron, and a little bit higher cobalt, a little bit higher nickel. I was able to correct my wrong statement by looking at the data, because it turns out that nickel is the stickiest of them all. It's got the most curved binding thing. And this is a physical chemistry thing. This is the pressure of the CO that they're putting over the framework, and then they measure how much CO is adsorbed. And you can see that when you get to zinc, it goes back down again. That also follows the Irving-Williams. Remember, Irving-Williams is like a little mountain. It peaks at Cu, and then it goes back down for Zn. So we're actually seeing that exact pattern. And you can see it for all of the physical chemistry things. They even have heats of adsorption. This is why I pulled it out, because it's Irving-Williams series, and it has a Q. Remember that Q is heat at constant pressure. So this is the binding of CO, forming that bond, and you can see that they can actually measure the bond distance. They can measure the heat that comes off. All of these things generally follow the same Irving-Williams series because they all have to do with how sticky that metal is. And so actually from this, one thing they don't address in the paper, but I could sort of address, maybe if they could put copper into that same environment, where do you expect it to be? Like we said, it's the peak of the Irving-Williams series, so it's the very stickiest of them all. So you'd expect copper to be even stickier than nickel. That's the kind of prediction that you can make. So the main thing I want to show you, heat, distance, these are things that you have been dealing with in the homework, and this is stuff that's actually in the in this paper right here. Don't let this stuff throw you on the right side. Only look at the left side. Look at the stuff you understand, and that's the key to looking at any paper. Honestly, there's always going to be stuff you don't understand, and don't let it bother you too much. Just make it so that you understand more when you finish reading than when you started. So what's cool about that as well is you can see that the distance goes down as the energy goes up, the heat released. The closer the bond is, and this is one of those things, by the way, if you ever are talking to a chemist and they want to test to see if you had a good education, they're going to ask you a question like this. They're going to ask you, like, if you have a bond that gives off more energy, do you expect that to be a stronger bond or a weaker bond? And people will usually say, it sounds like a weaker bond because it gave off energy, right? That means it lost energy. No, remember the bond is giving off energy because it is more stable. And the bond is a more stable arrangement of pluses and minuses, and it's therefore giving off energy when it goes into that. The energy is being given off by the system because it's so stable that it has the energy to spare. Maybe that's the way to think about it. It's a very common misconception, by the way, and we talk about it all the time at the conventions about how to teach it. So this is another example of that. Shorter bond, more energy given off. It's intuitive that shorter means stronger, so try to put things in that level. So that is the paper number 1. But I want to put this in the context of all of natural history, okay? So I want to return to this sort of diagram, which shows the biggest time scale possible, because time itself began 13.7 billion years ago. And the first thing that happened is there was a bunch of light, and the light condensed into atoms, and we had them clumping together and cooling down and forming the periodic table. There's something I wanted to put in the book but couldn't because I thought it was too much physical chemistry. Believe me, I do have my limits, even though you might doubt it sometimes when you read that book. But why would the atoms clump together, given the first law of thermodynamics and the second law, given all the laws, that energy can be transformed, but energy tends to spread out? Why would atoms clump together and cool down? Why would the universe ever reverse in entropy? Why would anything clump together at all? If entropy means spread out, and if the universe is constantly, if the entropy has to go up all the time, why did anything ever come together? Maybe that's the way to put it. So now we can also talk about entropy as a metaphor. Notice that there is a problem with the y-axis of this graph. The x-axis, there's no problem with it. This is an idea of how long, when you're a grad student, how long does it take for stuff to accumulate on your desk? And this is what's going to happen even as we move to more electronic stuff. Still tends to accumulate. And yeah, I had to clear out a space because I had a meeting yesterday with some collaborators. But I'm getting to the point where I'm like, okay, I need to do a entropy reduction program on my desk, but that's going to have to wait for another day because we've got teaching, we've got stuff to learn today. So, but the thing is, the dispersal of crap is what it says, is what entropy is. This is a metaphor. It's hard to find an explanation like with Boltzmann levels or with number. It's hard to put a number on this. Remember that entropy is a number. So this is funny, but it's just a metaphor. And now after this class, I want you to always know real entropy is a number. If you can't put a number on it, it's a metaphor. So entropy is always increasing, though. Entropy equals spreading out. But the usual thing that we said, and we said in class, entropy can decrease in the system if it increases in the surroundings. Okay, great. For example, you can talk about how does something ever crystallize? Well, something ever crystallizes because there's more entropy produced elsewhere, so the entropy decreases in the growing crystal. Okay, and this is exactly how it works in the case of crystallization, if you want to look that up. But we have a problem if we're talking about the whole universe. Because again, remember our whole thing about talking about the whole universe, there's nothing else. And so if we can't transfer entropy to nothing. By surroundings, we mean the rest of the universe. How do we solve this problem if there's no other place to put the entropy? So what we do is we want to put together like a model of the universe on the computer. We want to calculate what the entropy of the universe would be in the earliest parts and try to get a solution that allows things to come together while entropy is still increasing overall. Now we can recreate the sequence of creation, and it's actually surprisingly easy compared to how big the universe is. The fact that we can do this at all, I think, is one of the amazing things, and a lot of physicists will say the same thing. Einstein talked about the comprehensibility of the universe being a miracle. This is an example of that. You can basically take just a relatively simple computer model, and you can capture most of the important features of how galaxies formed, how stars formed, how planets formed, and things like that. And it makes something that looks like the universe that we can see. You can follow some of it after 2 chapters of PChem. So I want to show you a little bit of what that's about. I went back and I looked at their actual a paper that tries to talk about how fundamental physics can help you understand like a lot, even most of what's going on with the forming of astronomy. Now at the very end of class, you could read this. What I want to do is I want to focus right now on this right here. What they're doing is they're using basic physical arguments, but they're applying them to planet formation, which actually does involve chemistry. It's part of chemistry, and so this is physical chemistry. And they are going to predict how big different important objects in the universe are going to be using just a few fundamental constants. And what they end up doing is they end up calculating how big and small can stars be, neutron stars, a rocky planet, a white dwarf, and a typical galaxy. It's a huge variation in those objects, right? But they're saying we can have a relatively simple model that will give us reasonable answers that match what we see based on just the fundamental physics of how things come together. And this will show us that we understand those fundamental physics. There's not something huge that we're missing. By the way, dark energy is something else entirely, and it doesn't have to do with these objects right now. Dark energy has to do with how galaxies hold together. So there's still mysteries, and that's good. But these things, these are those different things, and these are the equations for the basic physical constants that will produce these maximum and minimum masses of these different objects. You can go through each of these. The main thing I want to show you, though, is they make it look fancy with all the Greek letters and subscripts, but there's really like 5 or 6 numbers coming together, and they're giving you reasonable ranges for the maximum masses of all these objects. It has to do with, it's related to particle mass ratios, the MP, and I don't remember what that is, but that's some physical constant that they're doing. The mass, it might be the mass of a proton, for all I know. That might actually be the mass of a proton. And the alpha has to do with structural constants, physical constants that have to do with how things go together. So too much physics for me, but what I want to do is I want to look up and down at these. These are very different objects, but they all can be related to these relatively simple equations. There's even a book I could have brought today called Just 6 Numbers. That's about how there's 6 numbers that cause the universe to be formed. And we can understand that. I never cease to be amazed at the fact that we can understand part of this universe at the same time that there's things like dark energy that show us that there's still lots of things to understand. So I want to remind you of these parts of Atkins as we go through. Again, whenever we have the different energy levels, you want to look at those and think about those and remember that we have this idea, the Boltzmann equation, for how particles will be distributed across those energy levels. Random distribution, and basically it's harder to get up to the upper energy levels. You can predict how many particles will be at each level at a given total energy level, given temperature. Okay? So these are pages that you've already seen. I just want to remind you that we have the Boltzmann equation for how many things get in the 2 levels that you're comparing. And then we had an explanation for how that relates to heat capacity. The heat capacity of something with a low heat capacity has a lot of spaced apart levels. Higher heat capacity has a lot of closer together levels. And that will result in the atoms vibrating differently, occupying the energy levels. Each energy level is a different vibration. And so as you get faster and faster vibrations, yeah, you have different energy levels. And the question is, how close together are they? And remember that we had the same explanation with energy levels for how increasing the volume increases the entropy. Now, we had this with the whole configurational entropy discussion that we had. And we talked about how when you expand the levels, they decrease in their energy. And so if you have the system at the same energy and you're increasing the volume, you get more levels that you can reach. You're bringing the ladder down in a sense, you know, so it's easier to climb up. So this actually has to do with the universe. But to deal with the whole universe, we have to ask the question of what is the spatial entropy of a volume that's expanding. That's one way to talk about it. Here's another way to talk about it. Remember that entropy has to do with probabilities. We had the Settlers of Catan example, right? Where we have the value of rolling a 7 on 2 dice is going to have a higher entropy than rolling a 2 or a 12, okay? This is the same kind of argument. It's just done with spaces rather than dice, spaces in a box. So let's say you have a box and you have, 4 spaces in the box, and each object can occupy just one space. You close the box, you shake it up, and you open it up again, and you see how the particles are distributed. You have exhaustively 6 possibilities. These 6 possibilities. But you're going to ask the question of what is the probability of finding both the particles on the same side of the box, on the left half or the right half of the box. So you can identify the ones where they're both on the same side. Here they're both on the left, there they're both on the right. All the other ones, there's one on the left and one on the right. There are 2 ways of being on the same side of the box. There are 4 ways of not being on the same side of the box. So right there, being on the same side of the box has a lower entropy. Being on opposite sides of the box has a higher entropy. And in fact, it has twice the entropy in this situation because there are 4 ways to be the one way and 2 ways to be the other way. So you can actually calculate the entropy is proportional to those fractions. The particles are 2 times more likely to be spread out. You're 2 times more likely to open the box and find them on opposite sides than the same side. And remember, this is a measure of entropy. Remember this equation, S equals K times omega, and omega is the natural log of W, so this is a slightly different way of doing it. Physicists always have to throw in as many Greek letters as they can, but this was the same thing that we saw. S is proportional to the number of microstates available. And so microstates can actually be thermal as well as spatial. This is a spatial explanation. The thermal microstates was actually the previous volume-based explanation that we showed you. But the thing is, entropy, as long as you define the microstates carefully, you can assign an entropy to them based on it.
Okay,
Yeah.
so the fourth one,
Yeah.
nothing close to each other.
Right.
Does that not count?
Yeah, you got to be real careful about how you're defining it. You're saying, are they just on the left side or the right side of the box? You're holding the box the same way, and you're defining the middle of the box as being right here. So technically, it's a different question if we say, what's the probability of finding the 2 next to each other? Then it becomes 50-50, right? But the probability of finding them both on the same side of the box is the 2 versus 4 example that we show here. That's a good example of things to see. With probabilities, it's always crucial that you look very carefully at that. So let's make a bigger box. Let's make a bigger box that has a volume V with n possible places to be. And so we can make a bigger box that looks like this right here. And we can have 6 particles in it. And there will be a certain entropy if we want to say, what is the likelihood of all of these particles being gathered together on one corner of the box as opposed to being spread out throughout the box? And the thing is, it actually gets exponentially more likely that they're going to be spread out. That first example that we had, it was pretty likely that they would be kind of close together. But the more spaces we have, the more likely that it is that they're not going to be touching when you're finished. If you have a bigger volume, then it actually is going to go up exponentially. And you can put this as an equation. The change in entropy for a conformation where you're increasing the volume, where the volume final is greater than the volume initial, so this number is a positive number, it will go through and the delta S will be a positive number as well. And it's actually going to scale by the natural log of the ratio. And by the way, this is the R gas constant. It shows up here as well as everywhere else. We're not going to talk about why, but I'll just show you that. So the main thing is, if there are more ways to arrange the objects in a bigger matrix, there's more entropy in it. They can be more spread out. So then realize that this is the entropy of spreading out in a volume. It doesn't have to do with the thermal entropy. The molecules can stay in one place in that volume, and they can vibrate and stuff like that. They can access thermal microstates. Well, it turns out this is related to what we've been talking about in class the whole time. You can actually write an equation that looks just like this. See this? This is configurational entropy. You can write a similar equation for thermal entropy, and it's just natural log of Tf over Ti rather than Vf over Vi in a different proportionality constant. C is just heat capacity. So the heat capacity equation is actually a thermal version of it's how temperature relates to entropy. This is how volume relates to entropy. And then we can also have temperature and volume related to each other, but we're separating out the components. The main thing is, deep down, we're talking about microstates, and these are compatible descriptions of microstates. We can layer them on top of each other. Deep down, thermal and configurational entropy are the same thing. You're just talking about thermal microstates as opposed to configurational microstates. They have different proportionality constants to convert the units from this form into entropy units. And so I want to bring back this paper. Remember to keep this paper in your file and to bring it to the test, because this is the really cool paper that shows it basically takes this equation and applies it to the heating of different elements, and it finds out that that entropy, the entropy of the substance, is related to the reaction, the delta H of the heating of that substance. So here's the delta H of heating, here's the entropy of that substance, and they form a line for all these 70 different experiments that they gathered. Realize that this goes also to the third law of thermodynamics, because we are integrating, when we find the S, we are integrating over the CP, over temperature range, from 0 to T. And the entropy of a substance is defined as 0. So we can say that there's a bottom limit to entropy, but entropy also will always be positive. There's a few physicists, in chemistry it'll always be positive. There's a few physicists that always like to mess with the chemists, and they come up with these quantum mechanical things, and they say, I've got negative entropy, and I'm like, great, but it's not chemistry. Yeah. Physicists and chemists do look at the world in a different way. Just remember that the equation that I want you to take away from this is this integral. This is the x-axis, this is the y-axis, and equation 3 shows the slope. Because if you take the x-axis equation, divide it by the y-axis equation, technically if you do it the other way around, then you will get this number. And you can see that by actually dividing the equations, and the data lines up with that exact slope. This is really actually useful. I want to show this phrase right here. This is a physical interpretation of entropy. It doesn't have recourse to disorder or randomness. It's all about heating. Now, the heating produces random movement on the lower level, but this is not a metaphor. This is getting you to the number. This is real physical chemistry, and this explains why entropy is a number. Okay, you can better bet. You better bet after talking about it for so much. I'm probably going to have something on the test that gets after this concept that you can choose to show me that you got this concept by saying it. I just want to say that there's hidden underneath this, remember that there's a heat capacity. The heat capacity is actually involved in both of these axes. And remember that heat capacity just has to do with those spacing of levels that we talked about. Diamond, for example, has a very low heat capacity. That's one thing I would not have expected, but if you have a diamond ring, you have one of the lowest, in fact it is possibly the lowest heat capacity substance that you can regularly get. Because it's so rigid, it's not able to hold much heat. The heat can't, the atoms are held together so much that they don't vibrate much when you put heat in. Copper is in the middle, lead is 38, although even those are on the low end of this graph. You get it really spread out when you get to bigger solids. But lead has a big CP. So we talk about diamonds and lead, they're sort of contrasting substances in a sense. Lead has a lot of loose or big atoms that are bound together sort of loosely, so it can move a lot. If you have a lattice that's bound together really tightly, it's going to have a low heat capacity. Something that is looser and bigger is more polarizable, and it has a higher heat capacity. All of these properties are related, and again, you don't need me to tell you they're related through the periodic table. Here's the actual data. You can look up your favorite. You can look up, they did uranium fluoride, it's like, and these are the references where they pulled the data from. But we want to get back to the question of how in the world did the universe ever cool? For an ideal gas expanding, the entropy of the system equals the different kinds of entropy that are present in the system. And we already talked about how there's configurational entropy and thermal entropy. And those both are equal to, the added up S is proportional to the natural log of the microstates. So remember that delta S is Q over T. That's our big equation from chapter 2. So if the system is closed and isolated, if there's nothing else but the system, there's no heat that can be transferred out of the system, so Q must be 0. There's no surroundings, then there's no heat flow to the surroundings. Therefore, it has to be 0. So as the configurational entropy, as the universe expands, its configurational entropy increases like crazy. So you can put some expansion energy into that, but there's no place for the heat to move to. So when a gas expands, the volume expands and the configurational entropy increases. If it's isolated, if you have a gas that's isolated, then the thermal entropy must decrease to keep the overall entropy constant. This is not the case with the universe, but it's the case with an isolated gas. Now the universe is pretty isolated, and you can actually model it. These computer programs that I showed you, they model it as an ideal gas. So all that stuff you learned in 1212 about ideal gases, you are actually learning how to model a young universe. You just didn't know it. Maybe we should teach it that way. It'd be more exciting. But the universe is, I'm trying to be ironic here, it is very isolated. It has no surroundings to exchange heat with. So as configurational entropy goes up, the thermal entropy of the atoms moving randomly will go down to keep the S the same. Except that there's one little wrinkle. Do you see the wrinkle with what I'm saying? So for an ideal gas, you will tend to see, as it expands, thermal entropy will cool down, and it will, as this goes up, that will go down because this has to stay 0. What's the one problem with applying that to the universe? What's the second law say about the S of the universe? Not that it's 0, but that's doing what? Yeah. So we've got a little bit of an issue, but the thing is, if you look at the math of the issue, the universe is expanding so much that it actually was expanding faster than the system. The numbers work out so much that the expansion was so great that the thermal entropy would still go down, and it still can be modeled as an ideal gas that it essentially has a delta S of 0. Okay? That is the one thing that So what about the second law? Okay. This equation actually doesn't equal 0. It's actually greater than 0. But if you look at the numbers, and you can calculate what the configurational entropy of the universe would be as it expanded. It expanded so fast that the delta S of the universe, the configurational entropy was huge, and that allowed the thermal entropy to do the thing that an ideal gas wants to do, the thermal entropy to go down. S configurational just has to be bigger than S thermal for S thermal to go down. So instead of going out of the universe, in a sense, the energy of the universe cooling went into the expansion of the universe. It went into the volume getting bigger rather than going into heat leaving the universe. But it still works as a second law as long as this is really big. So one of the things about the universe we have to have a universe that is not just expanding, but expanding rapidly enough that the rest of it can cool down. And that's a certain limit on how fast, it can't be expanding slower than the amount for stuff to cool down. And a huge universe actually makes sense because it makes the equations work. So some of the things, and people used to think the universe was smaller than it was, and now we know it's much huger. And some people say that it seems to be there's no purpose to it being so huge. Well, here's one purpose right here. It actually has to be huge so that it can cool down and still obey the second law of thermodynamics. You can only get that to work if S-conf is really big. And this is not an argument made by like eccentric scientists. This is an argument in the center of science for how we model those things. Anything cools when it expands. Entropy caused the formation of the stars and Earth because the universe was spreading out so much that it actually was effectively cooling down. Something had to cool down, and so the stars and the Earth cooled down and condensed. This is actually a quote from R.J.P. Williams himself. One of the things I want to do is occasionally give you Williams quotes. The cooling of the universe was a major cause of the natural selection of the chemical elements. I love that biological term put together. Actually, this is a physical term, biological term, and this is a chemical term right there. So you got all three disciplines right here. And by the way, it cooled so much that it actually cooled too much. We would have an ice rock here if it wasn't for the fact that radioactive decay of heavy elements, another manifestation of the first law, actually heats us up. We would not have been able to last 4 billion years at these relatively mild temperatures if it wasn't for this source of energy. And the Earth needed to stay around 300 Kelvin. We're going to use Kelvin units, so that liquid water could form. And I love this phrase. This is Williams. This is not me. The natural selection of the chemical elements decided that the only liquid on Earth's surface was water. And to have a liquid water, you have to have a warm planet. So that it leaves us with the universe. On Monday, I'll collect Chapter 2 homework, and Chapter 3 will be due. We'll start doing Chapter 3, and we'll continue to talk about water and phase diagrams and things like that.